Before going further, improving the optimality of our random variable estimator, we're going to take a little aside and talk about Bayes' rule. I'm sure you've seen Bayes' rule before, especially in the context of probabilities. In that context, we have that the probability of x and y is equal to the probability of x given y times the probability of y. And since there's nothing special about the ordering of x and y, we also get the opposite, that it's equal to the probability of y given x times the probability of x. Now, using these, and this is the format that most people encounter Bayes' rule, we get the probability of y given x is equal to the probability, or x given y is equal to the probability of y given x, probability of x, all over the probability of y. Okay, we're going to, in order to see how Bayes' rule actually affects probabilities, we're going to have to look at two things. First, what does Bayes' rule look like expressed in terms of the PDFs, or how is it manifest on the probability density functions? Here we have the joint probability density function of x and y, and that's just equal to the PDF of y times the PDF of x given y, and we're going to write it in this fashion. And as with the probability-based approach, we have some symmetry here. As an aside, if x and y are independent, we get some nice little properties. So independence implies that x given y is just going to be the PDF of x, and the PDF of y given x will just be the PDF of y. Using those either way gives you that fxy comma v is equal to f of x u fy of v, and that's not a surprise. We've seen that before, but now you can see where it ties in with Bayes' rule. Okay, now we can investigate what happens with expectations. Okay, we're going to start by finding the expectation with respect to the joint PDF of just x. And we can write that as an integral x fx. Let's go to our variables of integration. Like so, by definition. Using Bayes' rule now, we can expand this out in this manner. Well, by slightly rewriting this, actually give myself some room, we can come up with this expression. And note that this term in the middle here is simply the expected value of x given y and we can write it like that. We technically don't have to put in that little highlighted part there. It just helps us keep track of what PDF we're integrating against when we find the expectation. This should always be implied by the argument, but sometimes it makes things clearer. So now we're finding, in essence, using the outer integral, the expectation of Ex given y, but now with respect to y. So this can be written as the expected value with respect to y of the expected value with respect to x given y of x given y, like this. And of course it works the other way. Without going through the proof, this would be simply expected value of x, expected value of y given x, like so. Because the argument implies it, you will also see it simply written as the expected value of the expected value of x given y. And this is the same as that. Okay, so with that under our belts, we can go back and spend some time with our random variable estimation.